Okay. Our next speaker is Francis Howard, who will talk about Gertsch quotients. Please.
Thank you very much. And I will talk about the Gertsch quotients living in the poor man's adele's ring and some KurepaBellWilson relationships that we have. So in the outline, I'll review some Kuerpa factorials of Bell numbers, derangements, and we also look at some equivalences of Kuerpa from Vladimirov and some Argo identity and Kaneko, Masachusaki, and Seki. I'll also come to the Gertsch quotients and some special quotients related to this. So left factorials. So for left factorials, we will, for any positive integer n greater than 2, the left factorial is given by this summation from I from 0 to n minus 1 I factorial. And this factorial was defined by Kuerpa. And he conjectured that for n greater than 2, the greatest common divisor between the left factorial and the right factorial, the normal factorial, is always 2. Have been so many interest in this field, and some people have tried to give some equivalence related to this and try to do the proof. The proof is quite sophisticated, but numerically, most of the data can be found in OIS, which have been tabulated for 2 times 10 exponents and 40, which is quite a huge number, exponent 10 or so. In 1999, and Gertsch established uh, a mathematical equation that is linking the Kuerpa factorials, the Bell numbers, and she established that the Kuerpa prime P is congruent to the Bell, the P minus 1 Bell minus 1 mod P. Also, Mijalovic observed that for odd primes greater than 3, the Kuerpa can be defined in terms of derangement. So Kp should be congruent. I should use congruent to this mod P in terms of derangement. So from these two definitions or mathematical formulas, we notice that the derangement, the P minus 1 derangement, I call it the DER, is congruent to the Kuerpa, the Kp mod P. And also the Bell, the P minus 1 Bell is also congruent to the derangement plus 1 mod P. And this can also be found on the OES, the numbers for these can be found. Now, and Gertsch also conjectured that the Kuerpa is not congruent to 0 mod P. And she conjectured this to be part of the equivalence of the Kuerpa conjecture, that if this is also proved, then the Kuerpa conjecture is true. Similarly, if Daniel Baski also added that the Bell, the P minus 1 Bell number is also not congruent to 1 mod P. And if one tries to prove this, then the Kuerpa conjecture is also true. Some of the equivalence from Vladimirov is as follows. He considered two Bernoulli numbers, the truncated ones, and he named them VP and the VP star. I call these the atoms, Vladimirov atoms, just atoms as a name. And he gave a theorem that the Kuerpa conjecture is valid if the non-congruence for P equals, for odd primes, obeys this formula. Then, since 2002, when this was done, I got the opportunity to look at the paper. Then I did some investigation to see how this could also go. But it turns out that it's quite complicated to relate the Bernoulli numbers to the Kuerpa. and to see the validity of the Kuerpa from the Bernoulli numbers. It's quite complicated. So I moved on to look at how this connects to the Agor congruences. And Agor has some identities related to the Wilson and the Fermat quotient. So he has the identity of the truncated Bernoulli numbers, which is congruent to the Wilson quotient, mod P, and he has another identity. These are well-known identities that can be established with the glacier and also the glacier congruences and also the Wilson congruences. It can also be found in OES. It's well known. Now we move on to the Euler, the finite constant, the Euler, the Wilson constant, quotient, and the Mascheroni. This term was coined by Kaneko et al. And they introduced these finite constants to establish some quantities in the ring of A, which they call the poor man's Adele's ring. So we shall look at the poor man's Adele's ring from Kaneko et al. And also look at how he was able to get some examples of the quotients, Wilson's quotients, and the Euler finite quotients inside those rings. We extend these results to other quotients. So he defined the Euler of W to be the Wilson mod P for larger primes of P to be inside the ring A. Then he also defined the Grigori, the sum of the Grigori numbers, that G of n is the sum of the Grigori numbers, mod P, also to be inside the ring of A. Then he considered the Fermat quotient and he took the logarithm of x and he defined it as the Fermat quotient mod P for larger primes belonging to the ring of A, the Adele's ring, poor man's Adele's ring. Now he set L, small l of A of x to be x log of A belonging to A. Now, Kaneko, Machusaka, and Seki gave a theorem that the finite Euler constant of the M is equal to the finite Euler constant of the Wilson and plus the log, the finite Euler constant for the log of 2 minus 1. And equivalently, he showed that this sum is congruent to WP plus 2 Fermat quotient of 2 minus 1 mod P, where the summation of this is equivalent to 2 Q of P of 2 mod P, and the curl of the log is between 1 and -1 under A-B conjecture. So they proved this. Now, I give an equivalence of this just in terms of Agor's identity. So from Agor's identity, it is known that the sum of the truncated Bernoulli numbers, that is 1 over mk bk over k factorial, is congruent to the Wilson Wp plus the Fermat of m mod p. Now, if we add Fermat we add QP mod P to both sides of the equation, we end up with WP plus 2QP of M. If we take -1 mod P, like in terms of modulus from both sides, we arrive at this equation. Setting M to P in the ring of A, when we are in the ring of A, the Adele's ring, and we set M to P, we end up with exactly the equivalent identity that was proven in the theorem of Kaneko et al. So we just end up with this same theorem that Kaneko et al. Gave. Now, I move on to the Gertsch quotient and the special quotient. If there is any question at this time, I would like to know. Yes, if not, I continue. For the Gertsch quotient, we shall define for odd primes p greater than 2. We shall define the Gertsch quotient to be the Kuerpa, or the left factorial, minus the p minus 1 Bell number plus 1 over p. Now, with numerical simulation, it can be seen that the Gertsch P is an integer, and it has been done in the OES. And Miram also showed that this quotient, this type of quotient, is able to, it does not vanish. He has these quotients and he has seen that these are integers, and it can be shown that this does not vanish. Perhaps this is because the Kuerpa conjecture still must hold in this quotient. So I'm interested in the behavior of these quotients and sometimes how I can look at these quotients in the poor man's ring. So I give some few values for odd primes, 3, 5, or so, just to see for how the KP behaves. So the Kuerpa for these numbers are 434 and 874. And the Kuerpa mod P are, when we take modulus of the same thing, we have 146. This is also the same as the derangement as we established above, 146, the derangement mod P. Then the Gertsch quotients are just 96. So this details of this can be found on OES. A lot of sequences will be computed over there. Then we come to Argo-Guita conjecture, which is known. The Argo and the Guiga, yes, conjecture are well known. And for integers p greater than 1, we have that the p, Bernoulli of p minus 1 is congruent to negative 1 more p. And we know the Guiga conjecture also given as this. When we take when we take the Fermat quotient and we assume the Guiga conjecture holds, we can also define, let's define a quotient of the Bernoulli, the Bernoulli from the Argo conjecture, which is also well known. We define this quotient to be that equation 2. Then from this equation 2, we can have a special quotient. This quotient has already been defined by Argo in one of his papers. So we can have that the Q of P of M is given as this. And this is just the Argo-Guita notation that I have here, equation 2 plus the Fermat. Now, we define the finite Euler constants in A for the Gertsch quotients. And we have Gertsch GP mod P for larger primes belonging to the ring of A. We also define for L. L is Ledge quotient, and the Ledge quotient is just the summation. We know Ledge is just the summation of Fermat's quotient. So the Ledge quotient can also be defined to be in the ring of A. Following the relationship between Ledge and Wilson, we can define this. Then we can also define the special quotient and the Argo-Guita also to be in the ring of A, given in definition 6 as follows. Now we have a theorem for an odd prime P and an integer M greater than 1, with P not dividing M. We have that in the adele's ring, or in the poor man's adele's ring, we have that this summation is equal to the finite of the Wilson plus the log of M, and is also equal to the finite of the special quotient Q minus 1. We also have this identity that the summation in the ring of L, we also have this to be equal to this value, where the Fermat quotient of this is given as that. Now, when we subject M to be 2, we end up with these equations. Also, when we take M to be 1, we also end up with these equations. Now, for any fixed integer n, which is belonging to between 1 and p minus 1, we can also have that this sum, or this ring, also is equal to that, where the generalized harmonic number of order k is given as this. Now, the proof of this, we use the Argos identity, and the proof of this becomes straightforward from the definition of Argos identity, because Argo gave the truncated, already has given the truncated formula for the Bernoulli, truncated Bernoulli numbers, and combining that with the rings, with the Adele's ring defined earlier on, this becomes straightforward. And the consequences for m equals 2 and m equals 1 are also straightforward. Now, the next thing that I want to talk about is this theorem and this open problem. If we let A be equal to, so there should be an equal sign here, sorry for that. If we let A be the ring of A, that is the poor man's Adele's ring, and we let KP be the left factorials or the Kuiper factorials for odd prime P greater than or equal to 3, it is possible for one to see that the Kuiper can be defined to be in the ring of A. And this is given as that. Now, this brings us to a conjecture. And the conjecture is that for the Kuiper factorial, or for the Kuiper mod P belonging to a congruence to Bell P minus 1 mod P, if we assume the Kuiper holds for all prime, and also is in the poor man's ring, then the Kuiper mod P is non-zero. To prove this, we'll also need the Kuiper to also be proven. So in a way, I'm trying to look at equivalences that could help better understand the behavior of the Kuiper conjecture or the left factorials in terms of number theory, other forms of number theory or finite Euler forms. So this brings me to the end of my talk. The references can be found in this, and also an updated file can also be found on the archive. Yes. So thank you. If there are any questions.
Thank you very much. If there are any questions from Zoom, please speak up. You get some applause, but if there are no questions, I thank the speaker again. And the next talk will be in about 10 minutes.
Thank you. Okay.
We just have to see if our speaker will arrive. If you check the program or the abstracts or the list of speakers for the meetings, it has the email addresses of all of our speakers. So you can, if you have questions of any of our speakers, you can certainly send them an email. Where is our speaker?
Leaving. Are you 2:35?
It's at 2:30.
2:30?
Oh, hi.
Oh, Bobby, you're there.
Hi.
Can you upload your slides?
Yeah,
Share your slides?
okay, I have, should I, okay, wait. Okay, wait. Okay, let me, should I email them to you? I have them on my computer.
Well, you should be able to put them on your screen and share your screen with us.
Okay. Okay, let's see. Okay, wait. How come my picture's not showing?
I don't know.
Well, I could, so should I start sharing my picture? So let me, I'll start sharing my presentation, I guess.
Please.
Yes. Let me open it. Okay.